approximately 15,000 patients in a single outbreak. What do I mean by single outbreak is that I will explain later. And Singapore is a very small country with excellent system of environmental control. So in reality, you don't really see any mosquito compared to the neighboring country like Malaysia and Indonesia. But there are actually, even though we don't see the mosquito, there are actually far larger number of mosquitoes exist in that area. It's probably comparable with the, if you see a cockroach, then you know that just a single cockroach, then you know there are approximately 30 more cockroach there. So yeah, it's pretty much like that. And the Singapore government also do fogging system very often. Fogging is like putting some kind of chemical to kill just mosquito. So yeah, the air around you will be surrounded by fog and only mosquito will die. And they do it very often, especially in a place where mosquito often breeds, like in a sewer or in a place where there are often many stationary water. I mean, not flowing water, like after rain or and another interesting thing is that the Aedes mosquito in Singapore has distinct DNA strain from the one in Malaysia. So we might assume that the mosquito, and if we don't see mosquito that often in Singapore, so it might come from a neighboring country, which is Malaysia. And the fact that there is around 300,000 people of Malaysian going to and back to Singapore in a day might suggest that. However, the DNA strain is totally different, so we suggest that the disease itself is caused by the local mosquito, not by the foreign mosquito. And the pandemic occurs in non-predictable area. So we might also assume that the pandemic happened in an industrial area where, you know, the hygiene level is not very good and there are many mosquitoes breeding out there, or probably the place near the forest or something like that. But apparently no, the mosquito occurs in a like a normal housing area. So and it does not necessarily occur in a specific date of the year. We might also suggest that since they need the water for their breeding during the during the rainy season, which is around September to March in Singapore, there are more cases, but apparently that's not the case in Singapore. Some pandemic happens in any other time, so we are not sure yet about the environmental control. So it's not our concern right now. So then we suggest that the hypothesis is the virus is already there. I mean, there are many different reservoirs that can be activated at any given time. So there should be disease reservoir that allows such amount of human to get infected other than human and mosquito itself. And there are two different kind of reservoir here. So the one is subclinical human reservoir and stray animal reservoir. Okay, what's the difference between these two? And the human is, in the human, subclinical human reservoir means that the people who are infected but not going to hospital. So since the symptoms is very normal, you might think, oh, this is a normal cold, I don't need to go to hospital. But apparently, the people is infected with it, and they are not on track of government, because the government can only track the people who are going to hospital. And then for the case of stray animal factor, we suggest that another animal could contain another animal than human and mosquito could contain a dengue virus, but it's not that they will what do I say? They will transmit the disease directly from the animal to the human, but instead they make a large population of virus that's readily available for mosquito to transmit. So I will explain to the diagram next. Okay, about the interaction in this model, I'm just putting at 25 spots. It doesn't really represent anything, just spatial spots, and mosquitoes are placed randomly. And in this simulation, I did the population of mosquito is 10 times of the population of the human. Why do I put this? Mosquito become stationary because mosquito don't travel more than 500 meters in their life. So if let's say we divide Singapore by 25, the area would be larger than 500 meters definitely. So we assume that the mosquito is just stationary in that particular area. And human has the probability of moving randomly every turn. So I made every single turn to be 2 hours, and it's suited to the human activity. So let's say in the morning, in the morning and the early evening, human has more tendency to move from one place to another because it's the time of people going to school, office, etc., and going back home in the evening. But I put it around 2 a.m. the probability of moving to be 0, so just assuming that they are sleeping tightly in their home. However, the mosquito activity happens every single time, but on their peak period, they have the probability of contact is higher because sometime after the sunrise and sometime before the sunset, the mosquito activity is getting higher. And then, okay, here is the diagram. So we can basically start with any place. Let's say assume that susceptible mosquito bites an infected human. So in that way, the susceptible mosquito will get the virus from the human, and then the susceptible mosquito becomes infected. And the infected mosquito and then bites a susceptible human, and then the susceptible human become infected, and here goes the cycle. However, the human that become infected after passing through virus incubation period, they have certain probability to recover. So they can't recover after certain times because the virus won't yet. That's how the virus works, around 3 to 4 days, and then after that they can recover. So yeah, the probability of infection here is proportional to the number of, say for the probability of the mosquito to get infected is proportional to the susceptible mosquito and infected human, because the more infected human and the more susceptible mosquito, the more possible that the mosquito to get infected, and vice versa for the probability for human. Oh, sorry, I forgot to change it. It should be okay. This should be human, and this should be infected mosquito and susceptible human. So it should all be reversed. Okay, this is the result and discussion. This is just a plain modeling without any single reservoir. So and I'm just showing that the model works perfectly with SIR modeling, because yeah, you know that the actual okay. And then my task next is to compare the what does every parameter that I choose and how does they effect what is the effect of each parameter to the graphic itself. So here I will say that what I'm varying, and this part is if I'm varying the number to be higher than the normal, and this one is if I'm varying to be lower than the normal. Yeah. So if this one is the normal one, and okay, I forgot to mention you that the probability of the mosquito to get infected or the human to get infected is proportional to this is the number of, let's say, susceptible human and susceptible mosquito and infected human, or number of infected mosquito and susceptible human. Sorry, infected mosquito and susceptible human, or susceptible mosquito and infected human. Basically, the probability is proportional to this and divided by a certain coefficient that yeah, I mean, it's just a coefficient. So when I say that I increase the human infection coefficient, I'm increasing the k here. So we suppose that the probability of getting infected is getting lower. And what I notice is that when the probability is getting low, I decrease the probability by factor 10 here, and I notice that the pandemic doesn't occur. What do I define by pandemic is that there is a peak here, and in this case we don't really see a peak. It's just more like a stationary condition for a disease, I guess. And while when I I decrease this by a factor of 10, the rate of the number of susceptible and subclinical human becomes twice than the original condition. And this is I'm varying the mosquito infection coefficient. It means that how fast the mosquito to get infected, and varying this doesn't really change the effect on the human. So it might only affect the mosquito thoroughly, but it doesn't change the human, because if we see here, the number of human change very differently when you change the human infection coefficient. But when we change the mosquito infection coefficient, the number of human getting infected doesn't really change. It remains around 200 and something. And this is the peak time multiplier. It means that how active the mosquito during the active period compared to the normal period. And this time the multiplier here is 2 and this one is 5, while here is 1.2, and it doesn't really change that much. So it still remain around 200 to 300, but not very much. Okay, this is what I've done here at the moment, and some conclusion that I can make is that varying the parameters concerning the human directly has much more impact to the effect of human demographic. I mean, whether it's susceptible, infected, subclinical, or recovered. However, varying the mosquito parameter doesn't really impact the human. And then my future task is to finish coefficient comparison to fit the real condition. Because my problem now is with the real condition is that the Singapore population is about 5 million, while the peak could go about 7,000 or so, or at one peak, because 15,000 is from the whole peak, but at this very top, the vertex of the pandemic, there is about probably 7,000, and such number compared to, 7,000 compared to 5 million is very small actually. Comparing to this number, which accounts to 20% So my problem is how to make a small peak in a very large population.
Stop the SIR type model. That's the first step.
Okay.
Okay. Now it is the answer. I'll give
I
you
mean,
comment.
okay.
Yeah, conclusion, please.
So yeah, that's it. Because okay, I still do the SIR because
Actually, you are constructing SIR type model on source.
yeah I mean
Actually,
that was my original intention. But,
anyway, so your model is a huge. Okay, so I'll give you some comment. Human. Okay, S human, I human, R human, and S mosquito,
Oh,
I mosquito.
I don't have recovered mosquitoes. So.
Yeah, of course, but
Okay.
anyway, looks like this one.
Yeah.
Anyway, so and human mosquito infection process and mosquito human infection process both exist in the
Yes.
So maybe interacting SIR model. Of course, you are
Okay.
and
Yeah.
life processes. Okay. So anyway, SIR type model, N is increased. So they assume a random matching interaction process.
Okay. Yes.
That determines if N is okay, bigger and bigger and bigger,
Yes.
then infected percentage become 100%. So
Mm.
simply interaction is assumed in that type of model. Okay. So actual process is not a random interaction
Yes.
because every interaction is segmented. Okay. In realistic situation.
Okay.
So SIR type model assume a random matching. That is a point of bigger infected.
Okay.
Yes. So you have to change that one.
Okay.
Random matching is a very no realistic
Yeah.
assumption.
Okay.
And also in your approach, well, so vector type approach. So when in the case of for example, flu, seasonal flu or swine flu,
Okay.
only human and human interaction is assumed. But this type of dengue fever or West Nile fever, also there are vector and the human interaction process model is required.
Okay.
So for that type of model, you extend that double SIR model, but it looks like a double SIR model. Okay. But well, for example, in the case of West Nile fever, so mosquito and human and also I don't know how to bird, mosquito, human.
Okay.
So this actually in the case of dengue fever, link is only here or you or another hidden vector exists. That is a problem. You mentioned that first.
Yes.
So this for analyzing these type of hidden vector, so you need some methodological statement, a methodological approach.
Okay.
So at first, as you said, several characteristics in dengue fever. That means so at random that kind of things happen.
Okay.
And time is not determined.
Yes.
As mentioned. And several type of statistical pattern exist. So at first you should explain this type of pattern in realistic cases. So 5 million and 7,000 or that kind of data at first you should explain.
Okay.
And also what kind of model can explain or can make a similar type of patterns in that model you have to show.
Okay.
So for that purpose, you have to start from, of course, this type of WSIR model is out of scope because they assume that kind of interaction.
Okay.
So from an agent-based point of view. So starting from more segmented models, the interaction is limited.
Okay.
Okay, so maybe mosquito groups and human groups interact locally and move and locally and locally and locally.
Okay.
That model is first step required. And the second step, vector and human interaction model with agent base can explain that pattern or not. That is the first question. Of course, in this type of model, so mosquito life, in this case, vector is mosquito. In this case, mosquito is some seasonal pattern there might be exist.
Okay.
So some assumption we add to this first type of model. Then this type of pattern can be explained or not. That is the first question, okay? First research program. And the second one is if some additional assumption with vector human agent-based model cannot explain why it is difficult to explain by using this type of model. Then you introduce some hidden vector. But in that cases, of course, different type of hidden vector exists. For example, mosquito and human and this interaction, and also another vector interact here, no interaction cases.
Okay.
And also bird, like a West Nile fever cases. Birds, human no interaction. Birds, mosquito interaction. And mosquito, human interaction. That kind of case there exists.
Okay.
So what kind of hypothesis you have introduced, then you can create that kind of pattern. And last research program is, this is methodologically important. By using this type of approach, if you clarify what kind of hypothesis is suitable to explain that kind of realistic pattern, then this you have, then, so next research program is, realistic research. So by using a simulation model, what kind of vector or what kind of additional hidden vector should be clarified if you say in that model. Then go back to real research and try to find there exists realistically that kind of hidden vector exists or not.
Okay.
By using this simulation program, you can say we should try to find what kind of real hidden vector we should try to find.
Okay.
So this might be the output of this type of research. So that kind of methodological aspect you need. Okay. At first, give up.
Okay.
And second, this stage, and third stage, and last. This type of research program you should design. Okay, this is my comment. And another person.
I hope no one makes another comment.
I have a question about the data. You mentioned that the amount of people infected is 15,000, but you also mentioned that it is very hard to measure.
No, not 15,000. Okay. Oh, 15,000, yes. Okay.
But my question is like, because many people get infected and they don't go to the hospital, so that is very difficult to estimate.
So the 15,000 is because in my previous case, the model was about, this is susceptible, this is infected, this is subclinical, and they become recovered. So the 15,000 is the infected which goes to the hospital. Okay.
Yes, thank you. Is there an estimation about the number of infected people that don't go?
No, we don't have yet. The purpose of doing this is that we see whether the number of susceptible person is reasonable or not. So I mean, if we found that the number of susceptible person is not reasonable, then it might not be the case.
So, I have a question. For the pandemic disease, we must have a transmission sealant. But in your model, so does it have a transmission sealant, or does the problem occur in every month of the year?
This model just says, I just want to simulate during the pandemic time.
So you didn't consider time.
Yeah, so it's like during the case itself.
I know that even for the SIR model, we must consider the time.
Yeah, I mean it happens in 1 month approximately, but it's not in a specific time of the year. So it's just saying that it is on the pandemic. Yeah.
The mosquito here transmit many types of virus, right?
Sorry, wait.
Not just the one types of.
Oh yeah, they're actually 4 kind of different dengue fever, but for the sake of simplicity, we just say that there is one.
And I heard that for the Singapore government provided vaccination to prevent such disease.
I'm not really sure about this because but okay, I'll check it later.
I'm sorry, I couldn't understand that equation. So please show again.
Okay.
With unit.
So I'm just previously I was saying that so let's say this is the human factor with state S, which is susceptible, and they can go to either I or S. Okay, and
No. Equation.
yeah, and the probability of going to S and I is this one. So and then this, I'm just saying that the probability is something proportional to the number of, say for the human infection, susceptible human to times the infected mosquito, because the more infected mosquito are there, they can infect more people, and the more susceptible human are there, the more possible of the infected human to be there. So it's like when there are some infected mosquito and there are more human, there are more interaction that could happen. And so in
So you multiple.
yeah, so I multiple them, and this is just a coefficient too. I think Manson has something to say.
Or maybe your model is pretty, can be described like this is 2 agents, human and mosquito.
Yeah.
And mosquito is randomly placed in,
Okay.
in the model.
Yes.
And human is randomly walking in the whole model.
Okay.
Right? So human and we infect mosquito and then infect human.
Yeah.
And the probability, if we can divide the human into 3 subset of susceptible, infectious, and recover.
Okay.
And mosquito is divided into subset of susceptible and infected mosquito. And then the probability of human to be infected will be can we calculate like this? The number of infected, the number of infected mosquito divided into the total number of mosquito.
I mean, in my case, the denominator is not that way because I'm just putting an arbitrary coefficient since.
So the coefficient in there is
arbitrary. No, it's not related with it. In my case.
Why? Because what kind of coefficient? Because in SIR model, the transmission rate and recovery rate, and then the probability of the number of infected people is calculated right by this, right?
Yes.
So in the same.
Hey, wait.
Yeah.
Yeah. Okay. Go ahead.
Okay. Because the interaction of human and mosquito happen in your case in a sport, right?
Yes.
So the probability of mosquito getting infected is calculated by the number of infected human
Okay.
in that sport divided into the total number of human exist in that sport, and calculated and multiply with the number of susceptible mosquito. In this case, this is the transmission rate here. Transmission.
No, I don't think it will work. Firstly, because you are, in that case, you are assuming that the denominator is also proportional with the infected human, whereas. Okay, how do I say it?
So in your K, what is K?
It's just a number that I assign.
No, this is wrong. That's wrong because in SIR model,
But we also determine the beta as long as we want, isn't it?
No, this is wrong.
We don't. I mean, isn't a beta is arbitrary coefficient?
Because if the random interaction happen in a sport which human and mosquito agent exist, then the number of the probability of the mosquito to get infected depends on the number of human, right?
Okay.
Number infected of human, and also the number of susceptible.
Okay, but I think this one is assuming that, you know, when
This is the very, the basic SIR model. And reversely, the number of infected human depends on the number of infected mosquito and calculated with the susceptible number of susceptible human.
okay.
So this is the right equations for the SIR model. You divide it into
Anyway, so there exists, so vector and the human interaction type SIR model, there exist. So please try to find that
Okay.
kind of research. Maybe that kind. Yeah. Anyway, but anyway, you have to change that type of bug approach to more micro localized approach.
Okay.
So because in your model, the coefficient K is just a number that you set by yourself. So it's so you first time you have to define the model, the SIR model, and
No,
if it's not this, then you can assume that there is some kind of
what I don't
unknown.
get is
unknown K here, and you find what is K.
no. What I don't get is, why do you divide the probability of mosquito to get infected by the whole human population?
Which one?
The denominator is a whole human population in the spot.
Yeah.
Okay. Why is the probability of mosquito to get infected becomes lower by the increasing number of human population in that spot?
This one.
Yes.
This is the, you know, the probability of mosquito to meet human, which that human is infected. Because, for example, if you have 5 people in the same sport, and it is 1 people who is infected,
Okay.
then the probability of a mosquito to meet an infected people is 1 divided to 5.
Okay, I see.
Is that right?
Yeah. But I think I did it like this before. However, my concern is that it's like assuming that every single mosquito must bite a human whenever they meet.
Then the probability is depend on how many people which is infected.
Yeah, I mean for my let's say for my case, the K is always lower than the number of population that can happen in a place, so that it's not like mosquito will always bite human. But
So you just take a small example. For example, in this place, in this sport, there are 5 people, and the 1 people is infected.
okay,
And then if there is 100 meat mosquito, then the probability of the mosquito to meet one meet infected human is 0.2.
yes.
So the number of infected mosquito is 0.2 multiplied with 100 and then to 20. This is the very basic of
Yeah, I
example.
understand that. But in my understanding, there shouldn't always be 20 mosquito at one time, because I mean at that rate, because the mosquito can actually choose has the preference whether to bite the human or not, and the human itself has the tendency to avoid the mosquito. So I suppose it's not that way. That's what I understand.
So you have to have more assumption on that SIR model, because
Yeah.
SIR model is that
Okay.
random. So yeah, this is the probability of which is normal. So if you want to you assume that there is another coefficient should be multiplied with this number. For example, because you claim that this not this proportional, then this should be another hidden factors.
Yeah.
So you have to find out that hidden.
Okay.
Actually, this is the basic of SIR model. And I don't think that your K, your run
Arbitrary.
yeah, the coefficient K that you just set it by yourself is, what is the K, the real meaning of K?
Yeah. I mean,
So you have
I
to
just
explain
interpret
it.
this like when you say that di over dt equals to beta times s. Yeah, I just interpret the K as beta here. I mean, beta don't really have any meaning, but
No, it's have to have some meaning.
it doesn't relate to the. I mean, it's just a coefficient in the SIR.
No, there's no. If you have a
It's like a
a
transmission
coefficient
rate.
of no meaning, don't put in your model. That's it.
Okay.
Anyway, you have to clarify more assumption.
Okay.
And actually, you have to handle 2 types of population: mosquito population and human population.
Yes.
And the mosquito, to treat a mosquito population, maybe you need more and more assumption. So because some regional spot there exist, and what kind of spot, how mosquitoes population is controlled, and how people meet the population, that places. If people are living in very good controlled area and there's no mosquito, no interaction, and even if so the places there exist so many mosquitoes, how one mosquito can bite so how many people, and then that kind of assumption you have to write down. Then it's become far from SIR model.
Okay.
So that kind of assumption should be required. And maybe, so that kind of assumption can explain realistic pattern or not is the first question. And second is, well, in that kind of additional combination pattern cannot explain realistic pattern, then you have to introduce additional hidden vector patterns.
Okay.
So to explain realistic pattern. That kind of research, methodology is required. Anyway, starting from SIR or SI-like models structure, to change that model more realistic. Why agent-based approach?
Any other thing to ask?
Question. Okay.
By the way, do you consider the types of the dengue fever?
No.
No.
Just assuming that
The only one type.
there are actually 4 types.
Yeah, right.
And it's like let's say A, B, C, D.
Yeah, right.
Yeah. When you get the A,
Mhm.
you're after you recovered by A, you're immune to A and B, but getting more severe from C and B. And when you get the B and recover from B, you're immune from B and C, but the probability, you're getting more severe from A and D. But I don't consider this first.
Okay.
What is the population of Singapore?
5 million
5 million. So
around.
every year, 15,000.
It's not every year. It's during their considered worst outbreak.
15 people is infected.
Sorry.
The number of infected people by dengue in a season.
15,000 is just in a single outbreak, but throughout the whole year there should be more than 15,000.
There's no kind of data.
No, I at least we at the moment we only concern on what caused that pandemic. How can the pandemic got that number?
So it's around 0.03%.
Yes.
Not much, right?
Actually, it's not much, but for Singapore, they are very concerned with that matter.
It is possible for a person get all types of such as a person get A, B, C, D, and break out a new type of
Possible. Actually, it's possible. But yeah, it's just of my concern at the moment.
Okay. Thank you for your presentation.
今日ちょっとこの後のことなんですけど